Hi everybody, welcome back to some more calculus practice. Today we're going to be talking about how to find the derivative for sine of x, or y is equal to sine of x, using this graph to the right. In a couple previous videos, I talked about finding the derivatives of certain functions, and here we're just going to be trying to use a graphical method in order to estimate this specific derivative as well. And eventually we're going to move on to cosine for some more trigonometric functions. So here we have on the right, we have our sine function where it oscillates around our baseline to values of -1 and +1. The cool thing about this, in order to estimate derivatives, if we want to find specific points, all we have to do is pick our x points that we care about. Let's say we pick these specific points going along this curve. And what we can do is if we can plot a tangent line, and what a tangent line actually means, it is a line that only intersects this one point near that specific regime. The slope of that line will end up being our slope or our derivative at that specific point. So if I plot a line that intersects with this first point, most likely, if you can actually calculate it and you can zoom in on it, this line will actually have a slope of 1. And so I'll plot that on the same graph in blue. And if we do the same thing at the next point, at this maximum, the cool thing about maxima and minima actually is they will have a slope of 0. Because this line that intersects it is a horizontal line which has a slope of 0. Now if we do the same thing for the next point here, this will actually have a slope of -1 because we're on a downhill. And the slopes will always range between 1 and -1. I just picked the points that will make it the easiest that actually have these values. So here we have a -1 slope at this specific point, and then we'll have a 0. And so if you actually do this for every single peak and valley and also intersection or node, then what you'll see is we'll have a curve that actually oscillates around our baseline again. And if we connect these lines, what we'll see is that we seem like we have another trigonometric function. And I'll stop it right around here. So actually, the derivative of sine of x is actually going to be y prime is equal to cosine of x, where we start at 1 and then we oscillate and make our periods going through and oscillating around our baseline. Now you can also prove this using power series, which I haven't done here, and that's a different way of doing it. But using a graphical approach to estimate it is also another way that you can do it on an exam if you don't remember equations. And so the other generic rule as well is that if you have y is equal to a sine of bx, so let's say you have a coefficient out in front, but you also have a coefficient inside of that sine term, the derivative of this will also be the a will carry on the outside. It's going to be cosine of bx. The inside term will stay the same, and then using the chain rule, you need to take the derivative of the inside term. And so the derivative of this specific example on the bottom, and just generic example that you can use for any single sine function, is going to be a times b times cosine of bx. Now, this will apply to any derivative of the function of a times sine of bx. Now if we do the same thing for cosine of x, what we can do is do the slopes of those specific points as well. And we'll get 0, we'll get -1, we'll get 0, +1, and we'll follow this pattern as well. Now when you actually draw this out, this oscillation is a little bit different than just a sine of x, right? So what we see here is that y prime is going to be the inverted sine of x, or negative sine of x. Because we start at 0 and we go to -1 instead of the +1. So we just basically flip the graph across the baseline. And again, for a generic example, if we have y is equal to a times cosine of bx, where a and b are any numbers or any constants, we'll see that y prime is going to be kind of the same, but it's going to be negative a times b times sine of bx. I hope you have learned something here in this video. Have a great day.